at these problems. I don't want to spend all day doing this, but if we need to spend a little time, I'm totally fine with that. I want to make sure that this makes sense to you. And I will tell you that the applied problem is also Coulomb's law related. So it's going to be more practice of similar stuff. All right, here we go. So, Henry, you had requested, was it question 3? Is that what you said? Yeah. Okay. Do you want to just know answers or want to make sure we got 1 and 2? Is that what you're saying? Yeah. Yes? So, somebody want to give me an answer for A that we can just like double check and make sure we're agreed on?
Yes.
Go for it.
For Q1 at 0.36 newtons, Q2 is negative 0.36 newtons.
Yep. So the force is 0.36 newtons. It would make sense that Q1 and Q2 have the same force on them, right? Yes. Q1 and Q2, because they are interacting, forces require how many objects? 2. And the force of A on B and the force of B on A are going to be the same. Now, when you plug that in, you get a negative. I don't know if you noticed that you get a negative. The negatives and positives when you're dealing with Coulomb's law do not mean this way or this way. Negatives and positives indicate attractive or repulsive. A negative, right? Are you with me there? In this problem, you have a positive 2 microcoulombs and a negative 5 microcoulombs. Is that going to be attractive or repulsive? Attractive. So a negative force means that it's attractive. Okay? One's pulling this way, one's pulling this way, but they are pulling together, right?
Some of the sources I looked at use the absolute value of the particle charges, but in the problem,
you
just look and see.
Yes. So honestly, when I write them out, I don't usually put the positives and negatives because I just know in my head it's like one more step you have to think about, right? Yeah. But if I know that there are different charges, then I know that they've got to be attractive. Yeah. Yes. But the positives and negatives do not indicate direction. In more, I don't say advanced, like the next step of this that we don't have to cover in AP Physics 1 starts involving like, okay, I've got this charge and I've got this charge and I've got this charge. What's the force that I'm feeling? What is this middle force feeling or the middle charge feeling? And in that case, if I've got one pulling this way and one pulling this way, they both might be negative. You with me there? So you have to like think about what the negatives and positives mean. Does that help a little bit? So you want to do magnitude and direction separately when you're talking about Coulomb's law. All right, number 2. So number 1, are we okay with that? Does anybody want me to go through like actually stepping through step by step? I can. Are we okay? Okay, question number 2 for part A. What did we get for an answer for part A?
Q1 I got 6.075 newtons. 7. Oh yeah.
7.5. I rounded to the 100th. Yes. Okay. 6.08 newtons. And the other one is going to be the same, isn't it?
Yes.
They're going to both be this because, again, it's Newton's third law, friends. That's all it is. Is it attractive or repulsive?
Attractive.
They're attractive. Yeah. Now let's think about what happens now. For part B, the 2 spheres are brought together and they touch, but then they return to their original positions. What's the significance of putting the 2 spheres together? The radius is 0 for a moment, but we're going to touch them together and then we're going to move them apart again. So what's the significance of bringing this one that's got a positive 9 microcoulombs and one that's got a negative 3 microcoulombs? We're going to put them together. What's going to happen?
They're going to shoot.
What are you going to say? Electrons are going to move, right? Because the extra electrons that are on that negatively charged one, do they want to be near each other, friends? They do not. They're going to spread out as much as they can. And by doing that, we're going to equalize the charge in both spheres. So you have one that's 9 and one that's negative 3. I got that right? Yep. What's the net charge from those 2 spheres? 6. So what charge will each one have? They'll each have a charge of positive 3 microcoulombs. So it's the same system, the same amount of charge, but the distribution is different, and that's what matters. We bring them together and then we separate them, and now do they have the same 6.08 Newton force? No. No, because the KQQ over R squared, now our Q's, instead of being 9 and negative 3, are what and what? Positive 3 and positive 3. Does that make sense? And 9 times 3 is a different value than 3 times 3. Yeah. So what's our force now? 8 what was it? 2.03? I don't. 2.03? Do you guys agree with that? I think that's right. I realize that I did something wrong in mine, but I think that you're right. Yeah. Yeah. Are we doing okay? Yeah. Hey friends, can I have you all listen so that you might learn something and I can hear also? Thank you.
Does this have something like similar with the concept of center of gravity? Like,
Kind of. I mean, I guess I've never really thought about it that way, but sure.
I mean, like, no, I'm asking, like, since if two objects of similar mass or even of different mass, they're attracted to the center of gravity of the system.
Yeah, I mean, I think
They're sort of pulled to that
yes.
point.
Yeah, so we've got like a distribution of mass
Yeah.
in the center of gravity question. You've got a distribution of charge in the questions like this.
Yeah.
But yeah, so yes, they are similar in that distribution process. And our calculus friend would think, oh, it's the exact same problem, right?
Yeah.
It's the same deal. We're just talking about, matter as opposed to charge. Yes. I just never had like put it together that way or articulated it like that. Yeah. Yep. Unless you have a system that actually tells you specifically, like this is the charge, it's located here, and here's the charge, it's located here, and this is the relationship. Does that make sense? Because otherwise you don't know where they're at relative to each other. So you can't say, I mean, you could say towards, I guess, but not really anything else. Does that kind of make sense? Yeah. So this is going to be now repulsive, right? Okay. How are we doing? We okay? Courtney, go.
So how do we know that they're gonna be equal after they touch?
Because the electrons don't want to be near each other, right? And so they're going to spread out as much as they can so that they can be as far away from each other as they can. So all of the extra electrons that are over here on this one, not all of them, but some of them are going to move over here so that you've got an even spread. Does that help a little bit?
So even if they're different objects, just assume that they would.
Yes. Yeah. Yeah. I mean, I am sure that a materials engineer would take issue with me saying that because they would have different relationships with the charges moving. But I'm trying to think of an example that I've experienced in any of my schooling where I've ever dealt with that. Does that make sense?
Yeah.
So from my experience, then I would say that for sure for something you would do, unless it leads you there, right? Don't be like, no, Miss K said it was never going to happen, right? Like, because sometimes physics 1 problems, like they like to throw weird curveballs to see how you deal with it. So don't be like really bullheaded about it, but in general, yes. No. Okay, should I flip it over? On the back. So the point of this was to pull it all together. Circular motion works with gravity. That's what keeps our Earth going around the sun. That's what keeps our sun going around the center of the galaxy. That's all well and good. That's also a force that we could think about keeping the electron going around the proton. The point of this question was to show you the relative strength of the gravitational force and the electric force going around a proton, of an electron going around a proton. So you're just calculating gravitational force, calculating electrostatic force. One of them is bigger than the other. I hope you find. Yes? Yeah. So to find the gravitational, you're just going to do Fg is equal to GMM over the radius squared. To find the electrostatic force, You're going to do KQQ over R squared. The radius is the same in both cases. And if you wanted to actually find it, if you look right down here, it's right here. It's hanging out right there. Yeah, I didn't mean to confuse you. You can actually figure out in terms of which one accounts for the most force. You can answer that question without knowing the radius because you can still find the relative, like you could find a ratio. So that's why I didn't put it in there initially. But anyway, so you can find the two forces. Did anybody find values for either of them? Yeah, the gravitational or the electrostatic force? That's what I got too. 47th, right?
Yeah, and for the electrostatic, I got 8.23 times 10 to the negative 8.
They're both pretty little, right? Which one's bigger though? By a little bit, right? Yeah, like 10 to the 39th time. Like it's a lot bigger. Yeah. So which one is the one that really keeps that electron going around the proton? The electrostatic force, right? The Coulomb force is what keeps us going around. What's that?
It's not just like.
I don't understand what you're saying though. Because
No,
because
yeah.
the gravitational force is what keeps us going around the sun, right? And that works for this. Like that is what keeps us going. And if it was not there, we would no longer be orbiting the sun and everybody would be sad. Okay?
No.
It's not the electrostatic force. Why not? What's that?
Because the charge isn't that big a deal yet.
Well, there are a lot of charges in the sun. And there are a lot of charges on the earth. But neither of them is significantly charged in a positive or negative way, right? We're pretty neutral, and the sun is pretty neutral when it comes to charge. And so therefore, any electrostatic force between the sun and the earth doesn't matter. So gravitation matters when we're talking planets and stars and that sort of thing. But absolutely when we're talking about how the electron goes around the proton, it's this one. Okay? And then part B says, given that the electron orbits at a radius of this, what is the velocity? How fast does it go? So this is using the circular motion stuff that we did before, right? This is just plugging it right back in. Did you get a value yet? Or do you want me to walk you through this? Or where are we at with this one? Walk us through it, he says. The net force acting on the electron, given what we found in part A, the net force acting on the electron is really what? What force is it? It's really just the electrostatic force. And is the electron accelerating? What kind of acceleration is it experiencing?
Centripetal.
Okay, so let's do it. Yeah? We got this. We know the electrostatic force. You found it earlier. You know the mass. What mass is this? The mass of what? The electron, because the electron is the thing that is accelerating. And A sub C, oh yeah, that's just V squared over R. And oh, we know the radius is right there. So you can just solve for V. So V is equal to, it's going to be what? The square root of Fe times R over M. Did I do my algebra right there? I think that's good. Does that electron move fast or slow? Pretty fast. Yeah. Too fast? What do I mean when I say too fast? Faster than the speed of light. Anybody want to guess? Is the electron going to move faster than the speed of light? No, because it has mass. How fast does it go? Do we know? Velocity. Mm-hmm. What did you say? Just a little faster than you run? Yeah. Yeah, just a little bit. Yeah. How are we doing? Are we okay? Okay. All right. I am going to pause this so that we can go back and look at the applied problem. This applied problem comes from a lab, but the lab is kind of a like, we're just going to do it once kind of a lab. It's not